to the lecture of optimization. What is the purpose of optimization? In system identification, we are required to identify various parameters. One way of finding out the parameters is optimization. So it is a mathematical process of obtaining the best result under given circumstances. So we can use some mathematical tools for obtaining the results. In design, construction and maintenance of engineering system, we need to take certain decisions. Aim of this decision is to minimize the cost or maximize the profit. So a definition from Wikipedia. An optimization problem consists of maximizing or minimizing a real function by systematically choosing input values from within an allowed set and computing the value of the function. For this, we need specific methods to determine the best solution. We need to find a functional representation for the data and find a hyperplane to classify the data. Suppose we are having two types of data. So our aim is to find a best hyperplane which separate these two types of data. We have two types of optimization problem. One is unconstrained one, then the other one is constrained optimization. For unconstrained optimization, we will have linear regression. So definition. Optimization can be defined as the mathematical process of obtaining the set of conditions that give the maximum or minimum value of a function. That is the process of maximizing or minimizing a function. So we are given a function, we need to determine the critical point, maximum or minimum or saddle point. An example, let the short-run production function be q equal to 72L square minus 0.8 L cube. Find the value of labor which maximizes the production. So our function is given that q equal to 72L square minus 0.8 L cube. So our first step is we need to determine the first derivative. The first derivative of q is denoted as q bar. If we are having a function x raised to n, then derivative of this one is n x raised to n minus 1. So here we are having 2 as power. So 72 into 2 L minus 0.8 into 3 into L raised to power minus 1. 3 minus 1, that is equal to 2. So this one is 144 L minus 2.4 L square. So next step is we need to equate this first derivative as 0 and we need to solve for L. So 144 L minus 2.4 L square equal to 0. Taking L outside, 144 minus 2.4 L equal to 0. So either this L equal to 0 or this 144 minus 2.4 L equal to 0. So from this we will get L equal to 144 divided by 2.4, that is equal to 60. So we got L equal to 0 or L equal to 60. So now we need to determine f of x. So q of 0 equal to 72 L square minus 0.8 L cube. So substituting L equal to 0. So Q0 equal to 72 0 square minus 0.8 into 0 cube, that is equal to 0. Another value of L is 60. So substituting here, we will get 86,400. So we got the critical points. Here one point is 0, 0 and the other point is 60 and 400. Now we need to find f double dash of x. We need to differentiate this one, that is 144 minus 2.4 into L into 2 into L. So that is 144 minus 4.8 into L. So we need to do the second derivative test. We need to equate q double dash 0 equal to 14.4 minus 4.8 into 0, that is equal to 144, which is greater than 0. Since it is greater than 0, this point will be minimum. Now we need to substitute L equal to 60. So Q double dash of 60 equal to 144 minus 4.8 into 60. That is equal to minus 144. That is less than 0. Here it is negative. So it is less than 0. So this point will be maximum. So we got 2 points. Our aim is to find the labor of L which maximizes the production. So here we got maximum value for this one. Q double dash of 60, that is L equal to 60. So labor equal to 60 and the associated maximum production level is 86400. So another question. A firm's fixed cost are 135 and variable cost are 2Q per unit. Find the value of Q which minimizes the average cost. So total cost equal to fixed cost plus variable cost. So fixed cost is given as 135 and variable cost is given as 2Q per unit. So 2Q into Q. So we will get 135 plus 2Q into Q is 2Q the whole square. So average cost equal to total cost divided by quantity. So this is equal to total cost is 135 plus 2Q square divided by this Q. So this is equal to dividing, we will get 135 by Q, that is 135 Q raised to minus 1 plus 2Q square divided by Q. We can cancel 1Q. So we will get 2Q. So next step is differentiate AC with respect to Q. So we will get, differentiating this term, we will get minus 1 into 135 Q raised to minus 1 that is minus 2 plus with respect to Q we will get 2. So next step is to equate this to 0. AC dash equal to 0. So we will get 135 Q raised to minus 2 plus 2 equal to 0. So this is equal to minus 135 Q raised to minus 2 equal to 2. So we can move this Q to the next other side. Minus 135 equal to 2Q square. So Q square equal to minus 135 divided by 2. So taking the square root, we will get 8.216. So we got AC equal to 135 Q raised to minus 1 plus 2Q. So substituting the value of Q, we will get 135 into Q value is 8.216 raised to minus 1 plus 2 into Q value is 8.216. That is equal to, we got 32.863. So our critical point is 8.216. 32.863 is the critical point. That is, this is the fixed cost and this one is the variable cost. Now we need to find the second derivative of AC. So AC equal to second derivative means, so we need to differentiate first derivative. So this is our first derivative. So minus 135 into minus 2 q raised to minus 3. So this is the answer. Minus 135 into minus 2 we will get 270. So 270 q raised to minus 3. Substituting the value of q equal to 8.216, we will get 270 into 8.216 raised to minus 3. That is equal to 0.487, that is greater than 0. So actually it is greater than 0 means this point is minimum. So q equal to 8.216 when AC is a minimum of 32.863, this quantity. Another question, you have a production capacity of this much units. The profit equation for your product is shown below where quantity is in this and profit pi is in $1,000. How many units should you produce to maximize the profit? What is the corresponding profit? So it is given that pi equal to 5q cube minus 75q square plus 375q plus 500. So first step is to differentiate this pi. So we will get 5 into 3 q raised to 3 minus 1, that is 2, minus 75 into power is 2 q raised to 2 minus 1, that is 1, plus 375 into 1 power is 1, so into 1 q raised to 1 minus 1, that is 0. So we will get 15q square minus 150q q raised to 1, that is q, plus 375. So next we need to equate this to 0. So taking 15 outside, 15 into q square minus 10q plus 25 equal to 0. So we can factorize this term. Here we need to get a sum as 10 and product is 25. So it is minus 5 minus 5. So 15 into q minus 5 into q minus 5 equal to 0. So 15 into q minus 5 and q minus 5. So we can write it as q minus 5 the whole square equal to 0. From this we will get q equal to 5. Once you got the value of q, you can substitute in pi. So pi equal to 5 into pi cube minus 75 into 5 square plus 375 into 5 plus 500. This is equal to 1125. So our critical point is we got q equal to 5. So first point is 5, comma, next point is 1125. So this is our critical point. To find out whether it is a minimum point or maximum point, we need to find the second derivative. So second derivative of pi means we need to differentiate the first derivative value. First derivative value is this one, 15q square. That is we need to differentiate once more. So 15 into 2q minus 150 into 1. This is the answer. So we need to equate it to 0 and we can find pi double dash of 5 is equal to 0. Since it is 0, it is not greater than 0 or less than 0. But it is equal to 0. Equal to 0 means inclusive. So we need to perform the first derivative test. If it is greater than 0, we can directly write it as maximum. If it is less than 0, we can directly write it as minimum. So here it is equal to 0. So it is inclusive. So first derivative test means we need to choose two values. So this is a saddle point actually. We need to choose 2 points. And we need to choose a value below q equal to 5 and above q equal to 5. Because the slope equal to 0 at q equal to 5. So pi dash of 1 equal to 240 and pi dash of 10 equal to 375. So pi equal to, substituting the value of q, we will get q equal to 100. From this we got 100. So substituting the value of q in this pi, we will get this equation: 5 into 100 cube minus 75 into 100 plus 375 into 100 plus 500. So pi max equal to, you will get this one. So when selling this much units, maximum profit is limited by production, not by demand. So why do we need optimization in machine learning? All machine learning algorithms can be viewed as solution to optimization problems. So we need a basic understanding of optimization and deep understand the working of the ML algorithms. So rationalize the working of the algorithm, and we need to develop new algorithms based on the old algorithms. So we need optimization in machine learning algorithms. So consider a linear programming. So this is our formulation of linear programming. So this is our objective function, minimize f of x. This is objective function subject to g I of x less than or equal to 0 and h I of x equal to 0, where I equal to 1, 2, etc. m, j equal to 1, 2, etc. n, where x equal to x1, x2, etc. xn, and f g1, g2, etc. gm, h1, h2, etc. hn are functions on r raised to n. So the problem must be solved for the values of x1, x2, xn that satisfies the restriction and minimize the function. So we can formulate an LPP like this. So it is having objective function, then decision variable x, then there will be constraints. So components of the optimization problem is, first one is objective function. This is our objective function. Then decision variable, that is x is the decision variable, and constraints are g and h. So a maximization can always converted to a minimization problem using this equation. That is, maximize d of x equal to minus minimize of minus of d of x. Thus, the optimization problem can be taken to be a minimization problem. So optimization means we need to find a certain set of variables which either maximize or minimize an objective function. That is, finding out x which minimizes f of x. That is, find x equal to x1, x2, etc. xn which minimizes f of x. F of x is the objective function subjected to the constraints g, j of x less than or equal to 0, where j equal to 1, 2, etc. m. So we already told that conversion from one form to the other by multiplying with minus 1. So that is, here we are having the constraint x1 plus x2 less than or equal to 10. So multiplying with minus 1 means we will get minus of x1 plus x2, that is equal to, that is greater than or equal to minus 10. So here we are having two type of equalities, two type of constraints, that is inequality constraint, that is g, j of x, and equality constraints, that is L, j of x. So n is the number of variables. So here this x is a n by 1 decision vector and f of x is the objective function. M and p are the, this m and p are the number of constraints. So decision variable is subjected to different constraints, and these type of problems are called constrained optimization problem. The problems which do not have constraints are called unconstrained optimization problem. So find x equal to x1, x2, etc. xn, which minimizes f of x. So what is design vector? What is an x? How can we formulate x? Aim of the optimization problem is to find out the value of optimal value of the design vector which minimizes the objective function. That is, this design vector is related to objective function and constraint. It can be continuous, semi-continuous, discrete or set. An engineering optimization model consists of parameters whose numerical values are to be determined in order to achieve optimum design. For example, x equal to 2. X equal to 2 means there is no optimization. But if we wrote like this, x element of r raised to n, we need to choose the best alternative in Rn. For example, size, weight of a part, number of teeth in a gear, number of coils in springs are example for design vector. Design variables are collectively represented as design vector. This design variables means decision variables. Next is decision constraints. Are the mathematical function which define the interaction between the design variable. Decision constraints are written in terms of decision variable. So, in decision constraints, we will have decision variable. We have three types of constraints: inequality constraint, equality constraint, and side constraint. Inequality constraint means they ensure safety against a failure mode or satisfactory behavior under the given loading condition. That is, it will be of the form like this: Gj of x greater than or equal to 0. Then equality constraint means these constraints must be satisfied for design to be acceptable. It will be of the form Ej of x equal to 0. So example in case of structure mechanics problem will be like this. Then next is side constraint. So side constraints means we need to define the upper and lower bound on the decision variables. These constraints are also known as geometric constraints. Example, upper and lower bounds on number of teeth in a gear mesh is an example for this side constraint. Next is objective function, a function for which an extremum, that is minimum or maximum, is sought in the optimal design process. It is also called as merit function. Usually, weight, cost or volume of the structure are chosen as the objective function. Criteria with respect to which the decision variable are to be optimized is known as objective function. So, here we are having a two function x1 and x2. So, every solution in this variable space must be mapped to the objective function. That is our aim. So, we are having this function. Function is x1 square plus 3x2. So, every solution in this variable space must be mapped to this function. It can be continuous or semi-continuous. It can be bounded or unbounded. And there will be some absence of objective function also. That is, in unconstrained optimization problem, in presence of constraints leads to feasibility problems. Next is design space. The total region or domain defined by all design variables in the objective function is called design space. This is limited to constraints, otherwise we may have unbounded design space for which no feasible solution may exist. So here there will not be any feasible solution. Unbounded design space means there will not be any feasible solution. Constraints are useful in restricting the region in which the search for minimum or maximum decision variables are to be done. A vector x element of capital X satisfying all inequality and equality constraints is called the feasible solution to the problem. And collection of all such solutions form a feasible solution. The nonlinear programming problem to find the feasible point x star such that f of x greater than or equal to f of x star for all feasible point x, such a point is called optimal point. So we are having feasible solution and infeasible solution. Feasible solution means it satisfies all the constraints. Infeasible solution means it do not satisfy at least one constraint. Sometimes it may not satisfy all the constraints. Hard constraint, it must be satisfied in order to accept the solution. In soft constraints, some relaxations are allowed. A feasible solution is always preferred. An example, this is our optimization function, objective function. It is subjected to pi x1 square x2 by 4 greater than or equal to 300, and g of x is defined like this. So we are having two solutions, s1 equal to 310 and s2 equal to 86. So we can substitute it. Once we substitute it, we will get f1 equal to 7.05 and g1 equal to 70.69. Here f2 equal to 16.34 and g2 equal to 301.59. So here constraint is violated. Here the constraint is not violated, it satisfies the constraint. This one is a feasible solution and this is a infeasible solution. Next is bounded and unbounded problem. We are having an optimization problem. Objective function minimum f of f equal to 3x1 plus 2x2, f equal to minus infinity, x1 equal to minus infinity, x2 equal to minus infinity. So x1 and x2 can take a value minus infinity to minus infinity, and objective function is also minus infinity. So this problem is unbounded. And we have another problem. x1 can take any value between 100 and 700. It can take any value between 100 and 700. x2 can take any value between 100 and 50. 50 and 100. So bound on variables are 100 less than or equal to x1 less than or equal to 700, 50 less than or equal to x2 less than or equal to 100. So here f equal to 400, x1 equal to 100 and x2 equal to 50. So feasible region is bounded. So this one is the bounded region. We need to locate the best solution and it will be in the feasible region.